Hello students, welcome to the second topic for Statistical Modeling for Business Analytics. Today we will talk about regression with a binary dependent variable. So first we will talk about, this is how the presentation will go. First we will talk about difference between binary versus continuous dependent variable. Then we will talk about the linear probability model, and we will introduce the ideas of probit and logit regression. We will again estimate and how to estimate the probit and logit models, and how do you infer the results of probit and logit models. That is what we will look at, and all of this we will again do it by referring to a particular application, which is we will look at whether there is any racial discrimination in mortgage lending. So first we talk about what binary dependent variables are. So far when we have been looking at the dependent variables in all of the examples that we have used, the first example was in multiple regression, where we looked at district-wide average test scores in school districts. We looked at how the class sizes may affect the performance of students in a particular school district, or when we looked at traffic fatality rates and beer taxes. In both of these cases, the dependent variable, that is the y variable, was continuous. So it could take any of a large number of values, and we modeled it as such. But what if y is binary? So in some cases you are not interested, you are interested in discrete outcomes. Okay, so either you might when you apply to a particular college, you may get into the college or not, and you suppose you want to know what are the factors that affect whether you will get into the college or not. So these factors may be things like your high school grades, it may be your SAT scores, or in the case of in the Indian case, it may be your CAT scores or GATE scores. It may also be relevant to what your demographics are. Another such question might be whether a particular person smokes, or they take up smoking, or they don't. So this may depend on the price of the cigarettes, which may also depend on the level of taxes on the cigarettes. It may depend on the income of the individual, who whether they can afford to smoke, and it can depend on other demographic variables. In this particular lecture, we will discuss this example, which is whether a mortgage application is accepted or not. So before starting with this example, I'll briefly describe what a mortgage is. So if you own a house, or if you own some real estate property, and you want to get a loan based on the using that real estate property, or using that house as an asset, you would tell the bank that you can keep this as a security, and I want a loan for some immediate needs. That is called a mortgage. So when you apply for such a mortgage to a bank, the bank may accept your application and give you the loan, or they may deny the application and not give you the loan. So why may they deny your application? If they feel that even though you are offering a security, your ability to repay the loan is not high, and you may eventually, you may not be able to repay the loan, and you will become a defaulter. In such cases, you may want to see, if someone is looking at this data, they may want to see what are the factors that affect a bank's decision to deny or accept the mortgage application. So suppose you are interested in seeing what are the factors that affect this. This might be the income of the applicant. It might involve the characteristics of the house that they are putting up as a security. It may depend on their marital status, whether they are married or not married. It may also depend on things like their race. So this is another case where you are looking at either it gets accepted or it gets denied. Here, either they smoke or they do not. Here, you may get into college or not. As you can see, in each of these cases, the y variable is binary. it does not have, there is nothing like half getting into college or half smoking or half mortgage application being accepted. So the particular example that we will take look at is the mortgage denial and race data set. This is a data set that has collected data in 1990 in the Greater Boston area. It has 2,380 observations, and this was collected under the Home Mortgage Disclosure Act, which this Disclosure Act basically says that banks have to disclose the details of the people who applied for mortgages and whether that application was accepted or denied. What are your dependent variables? Is the mortgage denied or accepted? And the independent variables are things like the income, wealth, and employment status of the applicant and other loan property characteristics. What other loans have they taken? What is the value of the property that they have put up for security? And also things like what is the race of the applicant, whether they are white, they are black, they are Hispanic, or they are some other race. So all of these factors may affect the denial or the acceptance of their mortgage application. This is the particular example we will look at. Now, logit and probit regression, or discrete dependent variables. Logit and probit are just two methods for estimating, but discrete dependent variables are a very important subset of research questions that many people may want to answer. So many times when you are looking at a particular individual, whether they do one thing or not, whether they save for retirement or not, whether they smoke or not, whether they get married or not, whether they commit a crime or they get into, they are incarcerated or they go to jail for something or not. Each of these things, when you are trying to look at differences between individuals, then this kind of the dependent variable or the outcome variable is binary, and that is when you use this kind of methodology. So how do you, the first thing that we look at, the first way of trying to model binary dependent variables is using the linear probability model. So we first say, suppose you were just to take your y, you use your familiar yi equals to beta 0 plus beta 1 xi plus ui. You take this linear regression model. But now you will notice that in the normal case, when your yi is continuous, what does beta 1 stand for? Beta 1 stands for an increase in how much will there be an increase in yi for a unit increase in xi. This is what beta 1 stands for, right? Beta 1 is delta y by delta x. But what does beta 1 mean when y is binary? So y can only take a value of 1 or 0. There isn't a fractional del y that happens for a unit change in x. So you get a fractional change in y does not make any sense. Let me draw this kind of data, and then you will understand. So in normal regression, you have your y-axis and you have your x-axis, and say your x-axis varies between 0 and say, suppose here we are talking of education, and here you are talking of say salaries or something like that. And education may vary from 0 years of education to maybe something like even as high as 30 years of education or 35 years of education. And salaries, suppose you say in $1,000, or it can vary between 1,000, 2,000, whatever per month, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, and of course it can vary a lot more. Okay, suppose we say $10,000. So this is 10, this is 20, this is 30, this is 40, this is 50, this is 60, this is 70, and so on. This is $10,000. So you have an individual who is who has say 10 years of education, and they are making something like $30,000. So this is one data point, right? So you have 10, x1 equals 10 and y equals 30. Similarly, you can have many other data points which are like this. But basically y can take any value, and if you fit a regression line through this, you may get a line that goes something like this. Okay, but here basically, even if you do not have data for every value of education or every value of salary, you can still say that in case you had such a education, you could possibly predict that you would get that value of salary. It makes sense to predict somewhere between the intervals, because education can also vary, even though typically education will vary by number of years or things, but salaries can vary in a continuous level. Okay, but suppose you have a discrete data, and y, this is for y equals to 0. Let us use and you have y equals to 1. So you get, and say this is your independent variable, which is, say, x equals to income of the applicant, and this is say income, x is equal to education. Okay, let us take another example. Let us say x is equal to education, and this is gets a job or not. So say for very low levels of education, that person may not get a job. So gets a job is 1. So getting a job is written as a job is 1, not getting is equal to 0. So you will have some people with low levels of education who are not getting, but there may be some people with low levels of with high levels of education also who may not have a job. Okay, but more number of people with low levels of education do not have jobs. But when you have high levels of education, some with low levels also may have a job. But as the number of education goes up, more number of people have jobs. Okay, so these are the number of years of education, and you are looking at not the salaries that they are making, but whether they are at all getting a job or not. Okay, so your data may be like this. Now, if you were to just fit a regression line through this, you may get a regression line which is like this. Okay, it's very similar to this. But now, what does it mean? So if your education jumps from here to here, and the beta coefficient you say is this, and your data goes from your predicted y goes from this point to this point. But what does that even mean? You do not have a y which is possible. You either have a job or you don't have a job. You cannot have 20% of a job. Okay, so this is what does y mean, and what does the beta 0 plus beta 1x mean when y is binary? You cannot, what does beta 1 mean, and what does beta 0 plus beta 1x mean when y is binary? And what does the predicted value of y hat mean when y is binary? For example, what does y hat equals to 0.26 mean? Okay, so you can't really interpret this kind of a result when you're a linear regression, when your data is binary. So first we try to do something so that we try to convert our dependent variable, which is binary, into an dependent variable which is continuous. And how we do that is by reinterpreting our dependent variable as a probability. So instead of saying directly that it is the absolute value of 0 or 1, what we say is what is the probability that it will take a value of 0, or what is the probability that it will take a value of 1. And as you know, when you probability is a probability of an event occurring is a continuous variable. It is bounded by 0 and 1. So either the probability of, if it will not occur at all, if it does not occur at all, then the probability is 0. And if it is certain that it will occur, then the probability is 1. And if you are sort of 20%, you feel that there is a 20% chance of the probability occurring, then it is 0.20. So now you can see that it is a continuous variable which can take a value of 0, 0.1, 0.15, 0.29. So it is a continuous variable and it is bounded by 0 and 1. So first we start with the most simple linear probability model, where we say that the y is the probability, the predicted value of y is interpreted as the predicted probability that y equals to 1. And this is important to note that in discrete dependent variables, we always take the value of y equals to 1. That is what we are modeling. However, you may model either, so for instance, if you are getting into college or not, you can model the fact that you have gotten into college, you can denote that as y equals to 1, or the fact that you did not get into college, you could also denote that as y equals to 1. Depends on what is the question that you are interested in. But typically you will say that if the event occurs, that is the event that you take as y equals to 1. And if this is a probability that y equals to 1, then the expected value of y given x is the different values of y multiplied by the probability of that value happening. So what are the two values of y over here? One value is 1 and one value is 0. And 1 multiplied by the probability that y will take a value of 1 given x, plus 0 multiplied by the probability that y will take a value of 0 given x. Okay. Now 0 multiplied by anything, this term disappears. So you just have probability of y equals to 1 given x. So instead of your familiar yi equals to beta 0 plus beta 1 xi plus ui, here on your left hand side you have probability that y will be equal to 1 given x on your left hand side. Now what will happen in the right hand side? Expected value of ui, and if you are using least squares assumption number 1, then expected value of ui given xi is equal to 0, right? So because the average mean for every value, the average mean across all values of xi, you hope to fit a curve that such that the average means will be 0. Expected value of ui will be 0, or ui will be uncorrelated with xi. So you have expected value of beta 0 plus beta 1 xi plus ui given xi, but this is just the same as, since expected value of ui given xi is equal to 0, so you just have the first part of this term, that is expected value of beta 0 plus beta 1 xi. And so you have on your left hand side, you have probability y equals to 1 given x is equal to beta 0 plus beta 1 xi. So this is your linear probability model. So this is when, when y is binary, the linear regression model yi equals to beta 0 plus beta 1 xi plus ui is called the linear probability model, because probability of y equals to 1 given x is given as a linear function of beta 0 plus beta 1 xi. The predicted value is a probability, that is expected value of y given x equals to some some values of x is equal to probability of y equals to 1 given x takes some values of x, that is probability that y equals to 1 given x. So y hat is the predicted probability. So basically now what it becomes is, here getting a job or not, it becomes the probability of getting a job. So for a given level of education, what you are now looking at is what is the probability of getting a job. You are not directly looking at y, you are getting at the probability. So you say probability of getting a job with low levels of education is low, and probability of getting a job with high levels of education is higher and closer to 1. And what is beta 1? Beta 1 is the change in the probability for a unit change in x. So now this beta 1, which is the slope, beta 1 hat, or beta 1 is equal to the change in the probability. So for this level of education, this was your probability of getting a job. And for if you increase your education by a little bit, this is your probability of getting a job. So the change in the probability. So probability of y equals to 1 given x equals to x plus delta x minus probability of y equals to 1 given x equals to x divided by delta x. How much does your probability increase if you increase your education by a little bit? Okay, so that is what the incremental probability divided by the change in the independent variable. So this is how the mortgage denial case where we were looking at, that was the example that we are looking at. So in our particular case, we are defining the mortgage being denied as a dependent variable. Hence, when the mortgage is denied, we put that y as equal to 1, and when the mortgage is approved, we put that y is equal to 0. And if we fit linear probability model, and here on the x-axis we take something that is called the payments to income ratio. What is payments to income ratio? So if you take a loan, then you will have to make your interest payments or every month, right? So now suppose you have taken a loan of $10,000 and you have to make interest payments of say $300 per month. Then 300 is your payments and your income is $10,000. So 300 divided by 10,000 is your PI ratio. So as your PI ratio increases, then your ability to make the payment, given that you need to use your income for other purposes such as buying food, paying for the education of your children, and so on and so forth, given that you have so many uses for your income, if a large chunk of your income goes away in repaying your mortgage loan, then your ability to repay the loan goes down, and the bank takes that into its consideration, and it says, you know what, if the payments are very high, I don't think you will be able to repay this loan, and hence they deny your mortgage application. So as you can see, it has some effect, not a very large effect, but it has an effect. So when you estimate this for the full HMDA data set, you get deny hat, that is your dependent variable. You're trying to look at what is the probability that your mortgage application will be denied. That is equal to minus 0.080. This is your intercept, plus 0.604 PI ratio, and these are your standard errors, 0.032 and 0.098. This is for a total of 2,380 data points. So now, as you can imagine, that this does not directly tell you that PI ratio goes up by 1 and deny hat goes up by 0.604. That is not how you interpret it, because probability of deny hat goes up by 0.604. So when your denied PI ratio is 0.3, then what is the probability of deny hat? That is minus 0.80 plus 6.604 into 0.3, that is 0.151. Now, if your PI ratio increases from 0.3 to 0.4, that is, instead of 30% of your income, the payment being equivalent to 30% of your monthly income, payment becomes equivalent to 40% of your monthly income. So then what is the probability that your application will be denied? Given this particular estimated equation, it will be minus point. Here there is a Actually, there is a problem over here, because here it is written as 0.80, but it is actually 0.080, and here also, here it is 0.080. Okay, so 0.080 plus 0.604 into multiplied by 0.4, and you get 0.212. So the effect on the probability is of denial is this minus this, which comes to about 0.06. That is, by 6.1 percentage points, your probability of being denied goes up when your payment to income ratio goes up from 0.3 to 0.4. So we look at the linear probability model, where now we include another independent variable. That is, we include the race of the applicant, which is we basically include a dummy variable which is takes a value of 1 if the applicant is a black person, or takes a value of 0 otherwise. Okay, we are trying to see whether there is any whether there might be any omitted variable bias. Now, the predicted probability of denial for a black applicant with PI ratio equals 0.3. So in that case, PI ratio takes a value of 0.3. So you put minus 0.091 plus 0.559 multiplied by 0.3 plus 0.177. So the probability of denial for a black person who has a PI ratio of 0.3 is 0.254. Now you keep PI ratio constant at 0.3, and you look at the probability of denial for a person who is not black, not for a white person, but anyone who is not black. So here this PI ratio is kept constant at 0.3, and you substitute all the values, and you find that the probability of denial is 0.077. So if you were a black person, your probability of denial was 25.4%, and if you are not black, your probability of denial was 7.7%. So the difference is 0.177 or 17.7 percentage points, and this coefficient on black is significant at the 5% level. If you look at the coefficient and the standard error, you can see that it is significant at the 5% level. Still, there may be plenty of room for omitted variable bias. There may be other variables that we have not included that may result in a omitted variable bias. So, the linear probability models probability of y equals 1 given x as a linear function of x. What are the advantages of the linear probability model? One is that it is simple to estimate and to interpret. One unit increase in x leads to beta 1 unit increase in the probability of y taking a value of 1. Now, inference will be the same as in multiple regression, and we need to use heteroscedasticity, robust standard errors. Now, what are the disadvantages? One of the disadvantages is that the primary disadvantage is that LPM may predict probabilities that can be less than 0 or greater than 1. So if you look at the LPM model, you are fitting a line. Now this line can predict values of probability which are less than 0. So over here, somewhere over here, for a PI ratio of 0.2, you are predicting a negative probability, and for a PI ratio of 0.75, you are predicting a probability which is greater than 1, both of which is not possible, right? You can't have a probability value less than 0 or a value greater than 1. So this is one of the primary problems. Another problem is that the probability seems to increase linearly. Now, one would assume that these probabilities would rise at a given point. It would rise a little high quickly away from 0, and when it is approaching 0, it would stop rising as much, and basically it would be an asymptotic curve. Okay, where it is approaching 0 gently over here, and it is approaching 1 gently over here. So let us look at But if you take a linear probability model, so this is what the change in the predicted probability for a given change in x is the same for all values of x. Okay, but that doesn't seem to make sense. So these disadvantages can be solved by using a non-linear probability model. And what are these non-linear models? They are known as the probit model or the logit regression. Probit regression or logit regression. So we will talk about these now. So probit and logit regression is, you have, with the linear probability model, you are modeling the probability of y equals 1 as a linear function of x. Instead, you want the probability to be increasing in x. So as x goes up, your probability should increase quickly, and as x goes down, the slope should not be constant. Also, the function should be such that it is bounded by 0 and 1 for all x. So we need a non-linear functional curve. And so here we talk about if we could find a functional form that follows the shape of an S curve. So let us look at what that functional form might be. So one of the forms is called the probit model. So the probit model satisfies these conditions. One, probability of y equals 1 given x is increasing in x for beta 1 greater than 0. Okay, so for a positive slope, it is increasing. Initially, the slope increases, and over here, the slope decreases. And also, it is bounded by 0 and 1. Now, what is the probit model? The probit model models the probability that y equals 1 using the cumulative standard normal distribution function phi z. Okay, if you remember the normal distribution function or the standard normal distribution function, we had a function that looked something like this, right? So we had the normal distribution function which looked like this, and the standard normal distribution function, it was centered at 0, mean was 0, and the standard deviation was 1. Right. Now, what is the cumulative standard normal distribution function? Basically, the cumulative normal standard distribution function measures the area under the curve, for any given value of x. Say x is equal to over here minus 2. What is the area under the curve at the point minus 2 to the left side of minus 2? That is the cumulative standard normal distribution function. So at x is equal to minus 1, what is the area under the curve which is to the left of x is equal to minus 1? This is the cumulative standard normal distribution function. Now, this distribution function, as it happens, follows an S curve. Okay, so the probit regression model is modeled as this. Probability y equals 1 given x is phi, where phi stands for the cumulative standard. It's something that transforms this covariate, this beta 0 plus beta 1x, it transforms it. And how does it transform it? It uses this cumulative standard normal distribution function. Okay, so beta 0 plus beta 1x is called the z value or the z index of the probit model. So how do you find out what is, you calculate beta 0 plus beta 1x and you look up the cumulative standard normal distribution table and you find out the values of phi's of different values of this z index. So suppose your beta 0 is minus 2 and beta 1 is 3 and x is equal to 0.4, then your z index is minus 2 plus 3 into 0.4, that is minus 0.8. And the phi of that, when you take the cumulative standard normal distribution for minus 8, as I said, for minus 2 it would be the area under this, for minus 0.8 it would be the area to the left side of minus 0.8. And what is that area? The area under the standard normal density to the left of z equals to minus 0.8, which is, you look it up over here, minus 0.8 is 0.2119. Okay, the area under the entire normal distribution curve is how much? It's basically 1, right? And as you move farther and further, and you are basically, the entire area will be 1. But under this point minus 0.8, it is 0.211. So probability Z is less than minus 0.8 is 0.2119. And this is what the standard normal distribution, exactly what I had shown over here. This is what is being shown here. So why use the cumulative standard normal distribution function? The S shape gives us what we want. Okay, so the cumulative standard normal distribution function looks like this. So this is what it looks like. If this is the normal distribution function, then the associated cumulative function will look something. It may not be exactly right, but this is what the cumulative normal distribution function will look like. Standard normal distribution function. So it follows probability of y equals 1 is increasing in x for beta 1 greater than 0. It is easy to use. The probabilities are tabulated in the cumulative normal tables. It's relatively straightforward interpretation. This is the z value, beta 0 hat, where once you estimate this beta 0 hats, what is the exact beta 0 hat and what are the beta 1 hats, x. This is the predicted z value given x. Okay, and beta 1 is the change in z value for a unit change in x. So if you use this in the HMDA, using the HMDA data, and you use data to estimate your function, then what you get is probability of deny hat equals 1 given PI ratio is phi of minus 2.19 plus 2.97 into PI ratio, because this is what you have found. You have estimated and found your beta 1 coefficient to be 2.97 and your beta 0 coefficient to be minus 2.19. This is minus 2.19 plus 2.97 into PI ratio. So probability deny equals 1 given PI ratio is this. There is a positive coefficient for PI ratio. Does this make sense? So as your PI ratio goes up, the amount you have to pay divided by the total income, the payment amount becomes a larger and larger part of your income. It may be possible that for people where the payment is a large part of their income, they may not be able to make their payments, as a result of which the probability of their mortgage applications being denied will be higher. So the beta 1 coefficient that is positive makes sense. So standard errors have the usual interpretation. Basically, we are trying to look at whether this, given the data, what the errors, standard errors for the beta coefficients are, and that will allow you to see whether it is statistically significant. Of course, over here it seems to be statistically significant. So for PI ratio 0.3, you take phi of minus 1.3 and you get 0.097. For PI ratio, when it changes to 0.4, then your phi of the z value becomes minus 1 and phi of minus 1 becomes 0.159. So the probability changes from 0.097 to probability of denial of the mortgage application changes from 0.097 to 0.159, and this is what we expect. Now, suppose you have multiple regressors. So far, we were just looking at the PI ratio, but if you have multiple regressors, then probability of y equals 1 given x1 and x2, two regressors, is phi of beta 0 plus beta 1 x1 plus beta 2 x2. So the way you calculate your z value or the z index, that is what changes in a linear fashion. But this is transformed by a nonlinear function which is phi, and you take the phi of that linear z value or z index. So beta 1 is the effect on the z score of a unit change in x, keeping x2 holding constant x2. Again, you can include the coefficient, the variable black, where it says it is 0.7081, 579, and that is how it will it will change your z value by that much multiplied by 1 for black. Okay, so and finally you have these things. You can predict your probit probabilities. You can use another command. Here it says spread probabilities PIRAT 0.3 white. So suppose your PI ratio is 0.3 and you are a white person, what is the probability that you will be denied? Here if you had written you were a black person, you would find the probability for that. So this is what you get. If you estimate using another variable, you find that the coefficient of that is 0.71. Is it statistically significant? It definitely seems to be so. And over here, the coefficient for PI ratio goes down. If you see before, the coefficient for PI ratio over here was 2.97, right? When you were not including the variable black. So there was some omitted variable bias here, and when you include black over here, the coefficient reduces somewhat, and if you include even other variables that might have an effect on approval or denial of the application, then these variables may change further. So what is the estimated effect of race? Suppose you keep PI ratio constant at 0.3. You cannot directly say that it changes the probability by 0.71, because as you can see, there is a nonlinear transformation of this entire linear equation that is going on. So what you will have to do is find what is the phi of that when for a certain values of PI ratio and black, and find the phi of another certain values of PI ratio and black. Here we are keeping the PI ratio as constant at 0.3, and we are just changing the race variable from 1 to 0. You find that for a black person it is 0.233, and for a non-black person it is 0.075. So the difference in rejection probabilities is 0.158 or 15.8 percentage points. There might be still room for omitted variable bias. Now we come to another transformation which is known as the logit transformation. In fact, many of you may have heard this term more than probit, but it's just a different transformation to take into account to arrive at an S-shaped curve which will have the correct properties, so that your slope will be, your probabilities will increase as x increases, or and also the S-shaped curve will be bounded by 0 and 1. So you will not predict probabilities of less than 0 or more than 1. So logit regression, what is the transformation we are talking of here? Logit regression models the probability of y being equal to 1 given x as the cumulative standard logistic distribution function. Here over in probit regression, we had looked at cumulative standard normal distribution function. Here we are talking of cumulative standard logistic distribution function, and that is written as capital F functional transformation capital F of beta 0 plus beta 1x. And how is capital F defined? It is defined as 1 by 1 plus e to the power of minus beta 0 plus beta 1x. Okay, so it is just another functional transformation, and if you transform it in this way, it will have a similar S-shaped curve. Because logit and probit use different probability functions, the coefficient betas, if you use the same data to fit a probit function or you fit a logit function, you will get different values of beta 0 and beta 1, just because the functional forms themselves are different. So we wrote, what was the logit function? We wrote the logit function as f of x is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1 x, right? That is the same as 1 by 1 plus 1 by e to the power of beta 0 plus beta 1 x, because e to the power of a negative power will just be 1 by e to the power of the positive power of that. So you multiply this over here and you get e to the power of beta 0 plus beta 1 x divided by e to the power of beta 0 plus beta 1 x plus 1. You just multiply this here, you will have e to the power of beta 0 plus beta 1 x plus 1 divided by this, but since the denominator it is divided by this goes to the numerator, and so you will have the functional form like this, which is what is shown over here. Okay, this is what is shown over here. Now what can you do? You can take, if you take this, so this can also be, so what is 1 minus probability of y given x? If you write 1 minus this, then you will get some functional form. Okay, so 1 minus, if you write probability of y given x is equal to e to the power of beta 0 plus beta 1 x by 1 plus e to the power of beta 0 plus beta 1 x. So 1 minus probability of y given x is equal to 1 minus this quantity e to the power of beta 0 plus beta 1 x divided by 1 plus e to the power of beta 0 plus beta 1 x, that is equal to 1 plus e to the power of beta 0 plus beta 1 x minus e to the power of beta 0 plus beta 1 x divided by 1 plus e to the power of beta 0 plus beta 1 x. So this and this cancels out. So you have 1 by 1 plus e to the power of beta 0 plus beta 1 x. So you have probability of y given x is this. You have 1 minus, so this is the probability of denial. Probability of denial. And this is the probability of approval, right? If you don't get denied, your mortgage application will be approved. So probability of y given x divided by 1 minus probability of y given x. These are known as the odds of your, this is known as the odds of your application getting denied. Application getting denied. And this is equal to e to the power of beta 0 plus beta 1 x divided by 1 plus e to the power of beta 0 plus beta 1 x, from here divided by this. So that is multiplied by 1 plus e to the power of beta 0 plus beta 1 x. You flip this over, divided by 1. So this cancels out. So that is equal to e to the power of beta 0 plus beta 1 x. So the odds of your application by being denied is just e to the power of the z value that you have, e to the power of beta 0 plus beta 1 x. Now you take log on both sides. So you take log of probability of y given x by 1 minus probability of y given x, that is log odds. These are also called the log odds. Okay, log odds is just beta 0 plus beta 1 x, because if you take log of this, you will just arrive at beta 0 plus beta 1 x. So this is what has been shown. This can be written as log odds is equal to beta 0 plus beta 1 x, and this is the logit transformation. Okay. So basically you are looking at this is how you state it, and if you estimate it, suppose you have beta 0 you get as -3 and beta 1 you get as 2 and x you get as 0.4. So beta 0 plus beta 1 x, which is the z index, is the value you get it as is -2.2. So probability of y equals to 1 given x is equal to 0.4 is nothing but 1 by 1 plus e to the power of minus of, notice this minus, negative of the z index, and the z index itself is negative, that is -2.2. So e to the power of plus 2.2, that is 0.0998. So why do we at all use the logit transformation if we do have the probit transformation? The reason is that logit is computationally faster. In practice, logit and probit are very similar, since empirical results typically don't hinge on the logit probit choice. Okay. So if you use theta again and you use the logit function again, this is the result. These are the results that you get, and you get the coefficient for PI ratio as 5.37 and the coefficient for black as 1.27. And this is how the two models, the predicted probabilities are very close. As you can see, they almost lie one on top of the other. The blue line stands for the probit model, and the logit model, the black line stands. Which model you will use is up to you. It doesn't make much of a difference. So next we will start talking about the estimation and inference in the logit and probit models.